Section 4.4. Our objective today is I can apply theorems and corollaries about isosceles triangles. So first of all, let's make sure that we all agree on some terms that apply to isosceles triangle. In an isosceles triangle, remember that two sides are congruent. So the two congruent sides are what we call the legs. Okay, so those are the congruent sides. The angle formed by the two congruent sides, which would be this angle, is called our vertex angle. And the angles opposite the congruent sides, which would be that angle and that angle, are called the base angles. Okay, and the third side here is called the base. Okay, so the two sides that are congruent are the legs. The third side is the base. The angle formed by the two legs that are congruent, remember, is called the vertex angle, and the angles opposite the congruent sides, which would be those two angles, are called the base angles. And again, remember, it has nothing to do with how the triangle sits. So if I had an isosceles triangle that was like this, and this side was congruent to this side, then this would be my vertex angle, because it's the angle formed by the two congruent sides, or legs. These would be called our legs. This would be our base. And then the angle opposite, the two angles opposite the congruent sides would be our base angles. Okay, so again, nothing to do with how it sits on the paper. It has to do with where the congruent sides are and where the base is. Okay. All right, so our first theorem is called the isosceles triangle theorem. Which you can abbreviate like this. Okay, and since it has a name, you can use the name instead of writing the whole thing out. But what the theorem says, it says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. Okay? So if two sides of a triangle are congruent, in other words, if we have an isosceles triangle, so we have some isosceles triangle where this side is congruent to this side, then the theorem says, if this is A, B, C, the theorem says the angles opposite the congruent sides have to be congruent. Okay, so then we know that angle A must be congruent to angle C. So in other words, the base angles must be congruent. Okay. Then from this theorem, we have three corollaries. And remember that corollaries are statements that are obvious because of the theorem. Okay? So corollary 1 says an equilateral triangle is also equiangular. Okay, and again, that makes sense because if I have an equilateral triangle, so all three sides are the same. So if I say that these two sides are congruent, then I know that this angle is congruent to that angle. But if I say that this side is congruent to this side, then this angle has to be congruent to that angle, and therefore all three angles must be congruent. Okay? Corollary 2 says that an equilateral triangle has three 60-degree angles. Okay, and so again, that's obvious from the picture above. If all these angles are congruent and there's only 180 degrees to divide among them, 180 divided by 3 has to be 60. Let me change this 3 to a written 3 so we don't get confused. Okay, so has three 60-degree angles. And the third corollary says the bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. So this is a very, very powerful corollary. This is super, super, super important. So put a star by it because this gives you a lot of information. So you have an isosceles triangle. Okay, so if it's isosceles, we already know that this side is congruent to this side, and this angle is congruent to that angle. Now this corollary says that if we drop an angle bisector, okay, which would make this angle, which would make this angle congruent to that one by definition of angle bisector, okay? And so then this point here is going to be a midpoint. And so if this is triangle A, B, C, then because of this corollary, we can say that segment AX is congruent, or actually we can say length of AX equals length of XC. Therefore, AX is congruent to XC. Okay? So we know this is congruent to this. Okay? And we know that it's perpendicular. So we know that angle AXB is a right angle. And so therefore then angle CXB is a right angle. Okay. And so notice that because of that, we this corollary, we can get a lot of information. And what other side has to be congruent? Well, BX has to be congruent to itself. So that is, so we know then a lot about the triangle. So again, that's a very, very powerful corollary that we will use a lot. And then our final theorem is the converse, okay, of the isosceles triangle theorem. And it says, if two angles of a triangle are congruent, then the sides opposite those angles are congruent. Okay? So this one says, if this is congruent to this, then we know that side is congruent to that side. Okay? So it basically says if angle A is congruent to angle C, then segment AB is congruent to segment BC. Okay? All right, so let's look at a couple of example problems. Okay? So first of all, if I have this triangle, and I know this angle is congruent to this side, and this side is at 3x minus 2, and this side is 16, can we find the value of x? Well, by the converse of the isosceles triangle theorem, these base angles are congruent, so sides opposite have to be congruent. So then 3x minus 2 has to equal 16. So add 2 to both sides. 3x has to equal 18. Divide by 3, x equals 6. So we get a value of 6 for x. Okay? Then example 2. If I have this triangle, and I know this side's congruent to this side, I know that this is a 65-degree angle, and I want to know this angle. Well, by the isosceles triangle theorem, since the sides are congruent, this side is congruent to that side, then the base angles have to be congruent. So I know that this is 65. So 65 plus 65 is 130, and I know x plus 130 has to equal 180, and so x has to be 50 degrees. Okay? All right, let's look at a proof now involving isosceles triangle. Okay? So given that segment AB is congruent to segment CB, and segment AD is congruent to segment CD, prove that measure of angle BAD is equal to measure of angle BCD. And here's our picture. We have kind of a diamond kind of idea here, where this is A, B, C, D. And this is angle 1, 2, 3, 4. Okay. So in this one, I know, let's kind of get an idea of where we're going here. Okay. So I know that AB is congruent to CB. So that means triangle ABC is an isosceles triangle. So therefore we know angle 2 is congruent to angle 4. And we know that AD is congruent to CD. Okay, so therefore we know that angle 1 is congruent to angle 3. Okay, and what we're trying to get is measure of angle BAD. So that would be this angle, congruent to this angle. Okay, so those angles are made up of angle 1 plus angle 2, and then angle 3 plus angle 4. So that's kind of an idea of where we're going. Okay, so statements and reason. Okay, so number 1, segment AB is congruent to segment CB. and segment AD is congruent to segment CD. And we can say that because it's given. Okay? Then we can say that angle 2 is congruent to angle 4. Or in other words, measure of angle 2 equals measure of angle 4. And we can say the same thing for 1 and 3. And that's by the isosceles triangle theorem. Which says if the sides are congruent, then the angles opposite those sides have to be congruent. Okay? Then I can add those together. So measure of angle 1 plus measure of angle 2 equals measure of angle 3 plus measure of angle 4. Okay? And that's just, all I did was add these two together and add these two together. So that's just the addition property. Okay? But then I can say measure of angle BAD is equal to, oops, I need my BAD, measure of angle 1 plus measure of angle 2. And measure of angle BCD is equal to measure of angle 3 plus measure of angle 4. And that is by the angle addition postulate. Okay. Then by substitution using line 3 and line 4, I can say measure of angle BAD equals measure of angle BCD. And that was by substitution. Okay. And we're done.